Okay, so we want to give a parametric description of the unit circle using rational functions. Okay, so let's go ahead and go to our unit circle here. And so let's pick a point that's on the circle. That's at -1, 0. And we'll just take some line extending over here. Let's say the slope of this is t. That'll also be our parameter. So that's our slope. So slope t. And this line is going through some point x, y. Okay, so let's investigate the slope and see if through that we can get an equation for this line here. So slope is equal to the change in y's over change in x's, but that's exactly, let's see here. So y2 minus y1 over x2 minus x1, so that's x plus 1. And then we can actually solve this, right? So we can solve this algebraically for y. So that gives me y is equal to t times x plus 1. Okay, so also note the equation of the unit circle. So that's x squared plus y squared equals 1. And so here's the idea. So we've got a y value. That's from our line, right? So we're going to plug that into our unit circle. That's going to allow us to solve for x. And we're hoping that some rational function pops out. Okay, so taking this to this, that's going to give us x squared plus, in for y goes this quantity. So that's t times x plus 1, quantity squared equals 1. So let's go ahead and square this out. So that means that we're squaring this and then distributing the t squared. Okay, so mentally, yeah, I just squared this out. So that gave me x squared plus 2x plus 1, and then just distributed the t squared. Okay, so now let's take a look. We have a couple terms involving x squared, so we can actually factor the x squared out to the right. So that gives me the following. And this, let's bring this to the other side because it doesn't involve x. I'm hoping to solve for x, and I want to complete the square. So let's get everything that's not x to the other side. Okay, so this will be a little bit more promising if I can get a 1x squared here. So I'm going to divide all the terms by this quantity here. Okay, so that seems good. That puts me in a position to now complete the square one step closer to solving for x. All right, let's see how this goes. So when we complete the square, we have to take half of this, right? Half of this linear coefficient and then square it. We'll end up adding that to both sides. So not too bad. If I take half of that, the 2 will cancel. I just have to remember to square it, right? So half this coefficient squared. And if I add that to this side, I certainly have to add it to the other side. So I had this from before. And then we're adding this as well. Let's see here. Maybe to save some time, let's go ahead and square that. So that's t to the 4th over 1 plus t squared quantity squared. Okay, it'd be nice to have common denominators here. So let's go ahead. We're going to get common denominators. Okay, so I think to get common denominators, it's really nice just to multiply by 1 plus t squared over 1 plus t squared. A little messy there, but you get the idea. Okay, so that seems pretty good. So when I multiply these are conjugates, right? This times this. So when I multiply, that's going to give me 1 minus t to the 4th plus t to the 4th over a common denominator of 1 plus t squared squared. I'm not going to multiply that out. And so those will cancel. That seems really nice. And so now I can just go ahead and factor this. We know when we complete the square, this will factor into the square root of this, which is x, exactly this plus, and then the square root of this, which is t squared over 1 plus t squared, quantity squared. That's equal to 1 over the quantity 1 plus t squared squared. Okay, so I'm going to go ahead and take the square root of both sides. And it looks like all I have to do is subtract this. But they already have common denominators, so that tells us I've got 1 minus t squared over my common denominator of 1 plus t squared. And so there is a rational function description of the x's on the unit circle. And now we can actually use this to get a rational description of the y's. So our next goal is to essentially just plug this into x squared plus y squared equals 1 and solve for y. Okay, so that's our next goal. So let's see what that looks like. Okay, so now we go here. So x squared plus y squared is equal to 1. And then in for x goes what we found from before, right? So in for x goes 1 minus t squared over 1 plus t squared, quantity squared, plus y squared is equal to 1. All right, let's see what happens here. So we want to solve for y squared, so maybe we'll subtract this. So that's 1 minus this quantity. Okay, so that seems good. It'd probably be smart to get common denominators here. So I'm going to do that next. And I think that 1 plus t squared over itself is helpful based on this. All right, so what do we have here? So that's 1 minus t squared squared over 1 plus t squared squared. Okay, so I've got a common denominator. I can now worry about expanding out those binomials upstairs in the numerators. So let's see what we have here. So we've got 1 plus 2t squared plus t to the fourth when I expand this out, minus 1 minus 2t squared plus t to the fourth when I expand this out. That's all over a common denominator of 1 plus t squared, quantity squared. And of course, we could distribute our negative and combine like terms. And let's see what we have here. So the ones are going to cancel. It looks like the t to the fourths will cancel. And I'm going to have 2t squared plus 2t squared. So that's 4t squared over 1 plus, looks like t squared, quantity squared. And so just by taking the square root. So y is 2t over 1 plus t squared. So it looks like we have our rational description of points, or the rational points on the unit circle. And so, yeah, on the unit circle, xy is equal to, so we found x to be 1 minus t squared over 1 plus t squared. And we found y to be 2t over 1 plus t squared. Now you can check this will satisfy x squared plus y squared equals 1. That might be a good exercise to check. And let's just do a little investigation of how this relates to the unit circle in terms of drawing it and whatnot. Okay, so for choices of t that are in this interval, so if t is 0, you see we land at 1, comma 0, right? So when t is 0, we land here. Now this is kind of interesting, and more to do with limits than anything, but still sort of interesting. So as t goes to 1, so the closer I get to 1 on t, the closer this curve gets to the y-axis. So for t between 0 and 1, I just make it from here to here. But then for t from 1 on, it takes in limit t to go to infinity to get here. Now it will go here in limit, but I'm going to put an open circle there. And so that generates the top half of the unit circle. And then for t, let's say from minus infinity to 0 exclusive, because we already have 0 here. So minus infinity to minus 1, we go here. And then to 0, we go here. So there's the bottom half of the unit circle that's open. Okay, so in this way, we generate the unit circle. So our goal now is to apply this to integration. So we're going to use a technique called a Weierstrass substitution. So pretty neat. And so we're going to compute this integral. Okay, so yeah, let's set up our Weierstrass substitution. And so essentially our goal is to write this and this in terms of our parameter t, but thinking of the rational parameter, right? So the way we describe points on the circle using the rational functions. So we want to let t, this will help with d theta. So let t equal the tangent of theta over 2. We're going to take the arctan of both sides. So this is particularly good. So this is good for t between minus pi and pi. So that's why that's a good choice. So yeah, for t between minus pi and pi, this is actually quite nice. So now we're going to take the arctangent of both sides. So take the arctan of the left, and that's equal to the arctan of the right. Of course, that those will cancel. Arctan of tan cancels. You get the function inside. Let's isolate theta, because again, we want to get rid of d theta. So 2 arctan of t is equal to theta. And so just by taking derivatives, so I've got 2 over 1 plus t squared dt equals d theta. So that's going to be helpful there. And then from before, we just want to recall the following. So sine of theta, we said, was equal to 2t over 1 plus t squared. That's going to help with this. Okay, so we're going to carry through with our Weierstrass substitution. So d theta is exactly this quantity. We have 4 here minus, now sine, we said was this quantity. Okay, so I'm not super thrilled about these complex fractions here. So let's just multiply the top and the bottom by 1 plus t squared over 1 over itself. That'll make that a lot easier. Okay, so if I multiply through and I cancel, I get the following. So it looks like I get 2 dt, so that's really nice. This is over 4 times the quantity 1 plus t squared minus, that looks like 6t, right? 6t. Okay, so this I am happy about. So it looks like 2 goes into all of these. So I've got dt, I've got 2 times 1 plus t squared minus 3t. Okay, let's go ahead and distribute that 2. So that's going to be 2t squared minus 3t plus 2. And let's go ahead and maybe factor out the downstairs 2 in hopes of completing the square. Okay, so this seems pretty good. So I've factored a 2 out of all 3 terms. I want to complete the square, so let's group those together. And so let's see here. So we want to take half of this and square it. So half of this would be 3/4, right? So half of that would be 3/4. And if I square that, that's going to be 9/16. Okay, for balance, we also subtract the 9/16 here so that the effective net change is 0 of this quantity. So that seems pretty good. So again, half of that squared, just going to double check. So half would be minus 3/4, squared would be 9/16. So that seems just fine. So let's go ahead and combine these and then factor this. So here I've got, looks like t minus 3/4 quantity squared. Now 1, I can think about this as what, 16 over 16? And so that looks like 7/16. Okay, so this seems pretty good. It almost reminds me of sort of an arctan form. So let's go ahead and make a substitution. Let's let u equal t minus 3/4. du is equal to 1 dt. And that's in a nice form. So there's a u squared plus a squared form. Okay, so yeah, we recognize this as an arctangent form. So we've got 1/2. So I need 1 over a. Now remember, this is a squared, so I need 1 over a. So a is going to be radical 7/4. So 1 over a. Again, that's a squared, that's a. Then arctan of u over a plus c, but we're gonna really clean that up a bit. So I've got 1/2. That's going to be, it looks like 4 over radical 7. Arctan of 4u over radical 7 plus c. So we're going to plug in u and then go ahead and plug in t. So this is 1/2. We've got 4 radical 7. Arctan of 4 times u. Oops, u was t, not u. So u was t minus 3/4. So t minus 3/4 there. Over square root of 7. And maybe we'll just clean this up just a little bit, and then we'll plug in t. Okay, so I'm hoping that's seeming fine so far. And then our next goal is to, of course, plug in t. Okay, so of course we want to recall that t was equal to the tangent of theta over 2. Okay, so that's just going to go in for t there. So we've got 1/2 4 over radical 7 times the arctangent of 4 tangent of theta over 2 minus 3 over radical 7 plus c.